Okay, we're going to try another video here. Sorry I have to shout, but that's just how it is to record evidently right now. We have an ellipse. It's an elliptical orbit. This is a planet of enormous mass right here at one of the focal points. So this is the semi-major axis. I'm going to call that distance A. It's like the big radius. This is the semi-minor. It's the small radius of the ellipse. We'll call that B. And let's say that at some point this is some mass. We'll call that, let's just pretend it's the Earth, and this is a satellite maybe that's going in some crazy elliptical orbit now. So one of the things I want to point out about this problem, it's a little bit trickier. You can't use forces in circular motion because we don't have circular motion anymore. So with this case, we can use another trick. Imagine you have a satellite at some random spot. Okay, so here's the mass of a satellite, and in this case, you know that there's a gravitational force directed straight. The gravitational force is always directed straight at the planet. So if we consider the planet as a pivot point, we know that there is no torque caused by this gravitational force. So in that case, we can say that angular momentum is conserved. So for this satellite orbiting around here, we could use angular momentum. Furthermore, gravity is a conservative force. So if we want to, we could consider the gravitational potential energy, and then we have energy conserved. So we could talk about kinetic and potential energy instead of the work done by gravity. So for this problem, we could say both energy and angular momentum are conserved. You might notice that there is a force acting on this satellite. So momentum of the satellite is not conserved, but angular momentum is, because this force causes no torque. Okay, so let's hit it. We've got angular momentum. Let's write it down. L initial is equal to L final. In this case, let's say it's initially at some orbit. We'll say mv radius initial sine phi initial. So that's its initial position. So maybe let's draw that in our picture so we can see this one. Let's pick two common points that are easier to deal with. So let's say this is our initial. This is our initial point, and over here, let's choose this as our final point. So notice in this case, we could use this impact parameter. It's kind of hard to see here. So this is the impact parameter. I'm going to erase part of the orbit so we can see here. So the orbit is going around like this. This term is the impact parameter. So whatever distance this is, we could call this c. It's going to be A plus c is the initial impact parameter. So that's this whole term, the impact parameter. So we can see that the initial angular momentum is mv A plus c. So we've got that. Oh, and this is the initial speed. I apologize. So let's review. We're initially in this position, elliptical orbit. We're calling this distance A plus c. We know that angular momentum is conserved because there's no external torque. This is the general equation for angular momentum of a point particle. We're assuming the satellite is very small compared to this Earth, so we don't have to use a reduced mass. We can learn about that some other time. So then we say, okay, mass times initial velocity times the initial impact parameter. In this case, right at this point, it's moving this way. Here's V initial. So we know the impact parameter is A plus c. In the final state, it's moving this way. It's getting closer to the planet. What do you think? Is it going to speed up, slow down, or stay the same speed? Probably speed up. So let's call this V final. So now we can write this is equal to mv final R final sine phi final. Again, this is our final impact parameter. In this case, that's going to equal mass V final, and in this case, notice the impact parameter is B. So that's the final impact parameter. So that's going to be B. We've written down angular momentum, and maybe you're wondering which mass should I use. In this case, we're talking about the mass of the satellite, and we're talking about the angular momentum of the satellite, so this should be of the satellite. It's going to drop out, so let's clean that up. And notice we get V initial times A plus C is equal to V final times B. We now know a relationship between the velocities. And while it's a little bit more complex if you choose some different points, in theory you could use geometry to figure out the velocity at any point in the orbit as long as you know one of the points. If you know the velocity at any one point, you've got the velocity at every point, because you can use this type of relationship. Like I said, it's a little more complex in some cases, but you get the idea, I hope. Okay, so we have a relationship between the velocities. Let's write down an energy equation, because energy is also conserved. Okay, this is a gravitational force, it's a conservative force, so we can write down conservation of energy. In this case, E initial is equal to E final. Well, what types of energy do we have? We have kinetic energy, plus we have gravitational potential energy, initial. And that should equal K final plus U final. In this case, because the satellite is so small, we can treat it as a point mass. Therefore, we can use translational kinetic energy. So we'd say 1/2 mass of the satellite times velocity initial squared plus negative G. Oh man, I messed up. Let me give some space here. I need a little more space. So the kinetic energy is going to be 1/2 mass V initial squared plus the gravitational energy, which is negative G mass of the planet, mass of the satellite, all over the distance between them. So in this case, initially, what is the distance between them? A plus C. Let me get out of the way. So initially the distance is A plus C. In the final state, we could say the final kinetic energy is 1/2 mass of the satellite. Oh crap. Look at this. This should be mass of the satellite. Agreed? This should be the mass of the satellite because we're talking about the kinetic energy of the satellite. Why? We're assuming the planet's so big, it's basically at rest relative to this thing. Okay. So we've got V final squared. And then we've got the final gravitational energy, which again is negative G ME mass of the satellite over the distance. Ooh, what's the distance in this case? It's not B, it's not C, it's this distance right here. So notice that distance is going to be B squared plus C squared square root. That's kind of cool. Again, things to watch out for. Notice for the same position we're using two different radii here. It's because in the angular momentum we use the impact parameter, the perpendicular radius. Whereas for the gravitational problem we use the distance from the two masses center to center, which is this. Also, make sure you get these minus signs. As we've discussed in another video, you know that that minus sign makes sense because as you get farther away from the planet, you become less negative, which is more positive, which is like you're getting to a greater energy. Okay, so in this case, something does drop out, the ms. We can at least get that out of the way. If you're not feeling the fractions, multiply everything by 2. And let's rewrite that and see what we get. V initial squared minus 2G ME over A plus C. Now we haven't actually solved for anything yet, but we have used our two main equations that we suspected we could use. Angular momentum, because no external torque, and energy, because no external work. The work done by gravity is conservative. We included that as a potential energy. So at this point, I don't know what we're trying to find, but maybe you know A and C and B, and then you're trying to figure out the speeds. Maybe you know the initial speed of a satellite or something, or I don't know what you want to figure out. But in theory, you could see that most of this stuff you could figure out. We'd probably know the mass of the planet. So you could figure out one of the speeds from having the other one or something like that. Two equations, you could have two unknowns, I suppose. You could figure out one of the speeds and maybe B. Okay. Let's just leave it at that for right now. I just wanted to show you how you might set up an angular momentum and energy problem in this case. A fun one, a fun variation would be to consider the ratio of the speed at this point and that point, right? You can figure out by what factor does the speed increase. You do the same type of problem, except you do this point and that point. Notice initially you're at distance A plus C. At the end, in that new problem, you would be over here, which is A minus C. So you maybe get a fun little result in there, and then you can take the ratio and see what V final is divided by V initial. And as you suspect, maybe you can see this right here. Look, if I divide this term by B, look at this. In this case, A plus C is much bigger than B. This is much bigger than B. So we would expect it speeds up, which is what we thought earlier. So that kind of corroborates what we were thinking earlier. All right, let's call that good.
Quack, 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 quack.